And for the first talk, the title is zkEVM, Compatibility and Equivalence. And I'd like to welcome Alex Gluchowski. Thank you. Is this the clicker? OK. Just a sec. Oh, I see. OK, hello. Hi, everyone. I'm very excited to be here. Welcome, DappCon. I'm from zkSync. My name is Alex Gluchowski. I'm co-founder of Meta Labs, which is the company behind zkSync. I'm going to talk about zkEVM and equivalence versus compatibility as concepts and how they, what trade-offs they bring. I want to start with introducing zkSync really quickly. That's a zk rollup that is going to bring the first zkEVM to mainnet in now under 45 days. zkSync has been the first zk rollup ever built for Ethereum. We introduced the idea of zkEVM last year, in the beginning of last year. We later raised a significant amount of money from Andreessen and other investors to implement this vision. And we opened the first public zkEVM testnet in January last year. It's now running very stably and about to be launched soon on the mainnet. The mission of zkSync is to accelerate the mass adoption of crypto for personal sovereignty. And every design decision in the technical space we approach from the perspective of this mission. So we'll walk through these slides and take this perspective again. And this is why we had to embrace zkEVM. We didn't actually have an alternative to this approach to scaling Ethereum, because zk is the only technology we have that can potentially reach infinite scalability without giving up the properties that make Ethereum valuable, without actually if you don't go for zk, you have to be restrained in the blockchain trilemma and either give up decentralization, like not have every transaction verified by every single Ethereum node, or you have to give up security and you have to trust some people with certain security trade-offs. And zk solves both problems for you completely. And EVM has become de facto lingua franca of what will become the Internet of Value. For basically all blockchains are now embracing EVM as the standard. And there are so many tools, services, libraries written for it that it's really hard to escape the ecosystem. You have to stay within the ecosystem. And if you stay within the EVM ecosystem, then you have heard about this dichotomy, whether can you go for full equivalence or is it sufficient to be just compatible? In fact, the dichotomy is slightly wrong. We have a full spectrum reaching between the full equivalence to just mere compatibility with some stages in between. Vitalik Buterin had a beautiful article a couple of weeks ago now, introducing several types of EVM approaches to EVM compatibility, putting them on this nice scala between performance and compatibility. And I want to walk you through them and give you some intuition on where the costs differences are coming from in terms of zk implementation, and then show where zkSync is in this on this landscape. So we will start. So we'll start with basically with type 4, with the bottom degree where we just have compatibility. On the source code level, you can take any code written for EVM environment, compile it for the specialized execution environment optimized for zero-knowledge proofs, and you get the maximum performance, but you have the least degree of compatibility. You get the maximum performance because you compile. This is how we do it. We compile Solidity first to Yule with native Solidity compiler. Then we use our LLVM compiler to produce LLVM intermediate representation. Then we compile it into the actual zkEVM bytecode, which is a RISC kind of opcode set optimized specifically to be proven in the zk environment. What it means is every instruction that we have in our opcode is selected in such a way that they are all pretty equal in terms of number of constraints which actually determine the costs of proving operation in the zk environment. So since all of them are equal, at each cycle we have to actually execute all of them. Well, we have to put all of them in our circuit. So the costs are equaling the essentially the sum of of all the opcodes that we want to use. So at each cycle we execute the sum of all the opcodes, right? So since they are relatively small, breaking down into most atomic pieces, the sum is going to be minimal, and then you can have complex programs compiled in a way that uses the opcodes in the most optimal way. So this gives you the sum is small, so the performance is highest. With types 1 to 3, in order to reach full EVM bytecode compatibility, you have to go for complex instruction set. So you have to actually interpret EVM opcodes in the zk, and the cost of each cycle is going dramatically up, whether you're using certain opcodes or not. Because in the EVM, we have some opcodes that are very heavy, very complex, and it would be really hard to interpret them in the circuit. So that creates a massive, dramatic boost of the costs in just going from source code to EVM compatibility. This is why we start zk Sync when we launch now on mainnet. We will be type 4 system, because for our mission, it's critical that we have an option to offer developers the highest performance, so that we can actually onboard millions of people using some use cases like social networks or gaming or just a lot of payments that will require you to optimize the absolute maximum out of your application to support the very, very low cost per single transaction. But it doesn't mean that we have to stop there. If we have some really powerful environment, we can always simulate lower complexity environments, right? So if you have a MacBook, you can always run some older versions of Windows, DOS, NIX systems from 70s. And this is what we're doing. So as a next step, we're going to implement a smart contract that can interpret EVM opcodes natively. This is going to be a lot more expensive, so the performance will go down, but will enable us to take certain applications that are written in EVM bytecode that, for some reasons, people don't want to convert and recompile for this environment. Maybe because they are already audited and you want to keep the absolute compatibility with the audit and do not do the re-auditing. Maybe because they are optimized in certain ways for, you want to keep them for historical reasons. You will be able to do it at the cost of having lower performance. As a next step, we will have to support the full API compatibility for all the precompiles and all the hash functions, all the cryptographic primitives of Ethereum, which is not very complex. In fact, we're going to support all the hashes in zk Sync from day one. The SHA-256, Ketchup are going to be there from day one, so we will only need to support the other precompiles, specifically the BN256 elliptic curve pairings, so that you can do recursive zero-knowledge proofs verification in zk Sync. But once this is done, we will be type 2.5 system, and we expect this to be probably by the end of year. And then if we go up Vitalik's classification, type 2 and type 1 are the systems that actually fully compatible, fully equivalent to Ethereum, in the sense that gas cost calculation would be exactly the same as in layer 1. And for type 1, it would also include the block root verification with full consensus checks with full block headers. Now, this degree of equivalence is actually By the way, a very, very important thing. Like, if we started with a higher level, if we started with EVM equivalence, we would not be able to go back, because you can always simulate something less complex on a more advanced system, but you cannot really emulate a Mac OS modern one on some old Mac. This would just not work from the performance perspective, right? But yeah, going up is actually counterproductive for layer 2s, because the different gas cost profile that we have in layer 2s is actually there to be, because the different operation in layer 2s cost a lot less than they cost in layer 1. And you want to reflect it in your gas metering in layer 2. Because if you don't do this, you're either opening yourself up to a denial of service attack vector, or you're just not giving people the sparing in the storage costs and the computation costs, which you could give them, because those types of operations are a lot less expensive in a properly built rollup or Validium, for that matter. So the type 2, type 1 systems could be useful if we wanted to prove Ethereum layer 1 itself, but that would also close you from the ability to use the ultra-optimized applications specifically designed for the zk environment, which will enable this million of users use cases. So this is why we expect zkSync to stay at type 2.5 level system. And that's it. I want to open the questions now, because I think questions are going to be most interesting.
Thank you. When playing with different EVM chains, namely mainnet on one side and like Arbitrum or Optimism on the other, there is a big difference that almost nobody is looking at, which is the assumption around block timestamp and block numbers and the regularity of these. Now, this doesn't show in the layers you presented or Vitaly came up with, but it affects things like governance and time locks and a lot of user application. So do you have any comments on this kind of feature, which are like more hidden, more user space, and how you want to implement them, basically?
So are you talking about implicit assumptions that blocks have certain duration? Because those are the implicit, right? Like blocks can actually happen anytime. On Ethereum, the next block in proof of work can be found like half a second after the previous one.
Yeah,
right? So
also the implicit assumption that the block timestamp is a monotonic function. On some rollups, like 100 blocks could have the same timestamps because they are anchored to the same L1 block.
No. In zkSync,
I mean, I'm not talking about zkSync. On some rollups, it happens like that.
So what's the question?
So how do you implement block numbers and block timestamp, and will that cause any compatibility issues with existing mainnet code?
Yeah, so that's what I'm saying. Like we at zkSync, we follow the Ethereum convention. So we have like blocks in layer 2 have their separate numeration. They're detached from the block numbering of layer 1. And the block timestamps increase monotonically, and they must be, like it's constrained in the zk environment that they have to grow up. So in this regard, we're following, like from the perspective of the application, there is no difference from Ethereum. Like the conventions are preserved, the invariants are preserved. Cannot talk about the other rollups.
Hey, Alex.
Hello.
Thanks for joining us. So I would like to ask a question about finality times. What are they today? What they will be in the future? And how difficult problem is that?
That's a great question. So we have, with any kind of rollup, we want the user experience to be better than what you have on layer 1, so transactions are normally confirmed faster. If you have a centralized sequencer, it's pretty easy. You can just always take a transaction from a user in your API and immediately confirm. Once we have decentralized sequencer, and we are at zkSync are working on it, we will be aiming for very short blocks, like ideally sub-second blocks, so that your transaction from the point of view of the user is confirmed immediately. The finality is reached, though, when you have a checkpoint on layer 1, and you, like in case of zk rollup, you'll provide the proof that this new state is actually valid. So you need to be able to generate this proof. There are two factors that influence the finality. One is how long does it take us to generate a proof for a number of transactions, for one or more blocks. Right now, this number is, for zkSync version 1, it's about 20 minutes for like a batch of blocks. For zkSync version 2, it's going to be a lot less. There are two reasons. One is that we're using a much better hardware. We're actually going to use GPU accelerators for proving that are much faster than using CPUs. And the second factor is that all the blocks are constructed recursively in parallel. So we only have a few levels of recursion, and each step of recursion is very cheap. So we expect the block generation times to go down to like potentially under 1 minute, and maybe even like at some point in the future, it will be like just a few seconds. So we would theoretically be able to generate the proofs for our blocks, like every Ethereum block. That is perfectly doable. The other question is it economically justified? Because a proof, zk proof on layer 1 needs to be verified, and the verification costs something like 500,000 gas, 600,000 gas for a snark proof, and we're using Plonk, which is a pairing-based snark. If we used Starks or like Stark similar systems like Redshift, Plonky2, it would go up currently to like 5 million gas. So you have to pay 5 million gas for a block of n transactions. So you have to amortize the cost of this block, of this 5 million gas, across all the transactions. If you only have a few of them, it would be too expensive per transaction. Right? So we want to wait for a block with sufficiently many transactions to make it justifiable. So right now on zkSync, this waiting time for version 1 is a few hours, but we're only doing simple payments. I know that Starkware, for example, has it like much longer. Like I think they're doing the checkpoints every like a few times per day, maybe twice a day. But I think that with zkSync version 2, especially with the addition of zk Porter, which introduces very, very cheap transactions, additionally to the rollup transactions, because you don't publish the data availability on chain, we will have a lot more throughput, and it will be a lot more justified to have like very frequent checkpoints, like every few minutes, maybe every 10 minutes. Like that's my guess, but we will only see it in the experiments. More questions?
All right, then. Oh, there is a question right there.
Yeah, thanks for your presentation. Do you guys, for the zkSync 2.0, support all of the geth calls? Or maybe you could talk a little bit about what you guys support or what you don't.
Sure. Yeah, that's the much easier part, because the geth calls, the Web3 API, is something the server can completely simulate. So yes, we will support close to 100% compatibility. Not 100% from day one, but we will get to 100%. Because there are also some nuances, like you also have hooks, you have other like more complicated operations, but all the basic queries work just exactly the same way as they work on Ethereum. So we're currently integrating Chainlink. We already integrated the graph. The graph is already indexing zkSync version 2 testnet by using the normal Web3 API. So you as a developer will be able to use the Web3 API directly, or using all the services that rely on Web3 API, like the graph, in exactly the same way. So it's, yeah, from developer perspective, it's fully compatible.
Still have a few more minutes if anyone else wants to ask.
So if we can, like, if talking about the tools generally, all the tools that read the state are going to be working out of the box. The tools that write the state are like from day one of zk sync mainnet. There are differences in the way, like, how you deploy contracts, because you need to compile contracts. So you cannot just take the same tools, like your like natural truffle or waffle or hard hat environment, and just keep using it, relying on the same Web3 API to push transactions. Because the bytecode, if you just keep compiling your contracts in Solidity to EVM, of course, this EVM bytecode won't be workable. That's why we have some plugins for the deployment environment, so that you inject an intermediate step in your scripts to compile Solidity into zkEVM before you actually deploy contracts. But like everything that reads code is the same, reads the state. The difference that will always be the tools that we won't be able to support staying at type 2.5. Like because of type 4, because of our source code compatibility and having to compile these things, is the anything that works at opcode level, like debuggers, tracers. Those things will never work out of the box. We will have to integrate them separately and work with the vendors to provide specific support for zk sync in order to support them. But those are like a very limited set of tools that are currently popular, and we will just be supporting all of them. So you will be able to use the same UI for the debugger, like Tenderly or like whatever you're using. But under the hood, you will just have different opcodes. And you will see these different opcodes. You will not see the EVM opcodes. You will see the zkEVM bytecodes. But that is like, I think most people, like I personally, always use console log over debugger. And this is what you always will be able to use, and just like re-execute the transaction from a certain state, in a certain position, changing the code, seeing what happens there. Like this is a lot more powerful than tweaking the opcode, like disassembly and trying to guess what happened there. Sure.
Just talking about the source code and the type 4 layer, you mentioned Solidity. Will you also be supporting Viper?
Yes, we do support Viper, actually. It's already working, yes. So we will support Solidity natively because it compiles into Yule, and then we have like close to 100% compatibility. We support Viper by compiling Viper directly into our, we have an LLVM frontend for Viper. So we compile it directly into this intermediate representation, but it works well. And then we will be able to add LLVM frontends for existing languages that already have LLVM frontends. Like all the modern languages have it. Rust, Golang, C++, Python, like whatever you want to use. Of course, you want to use the language that is most suitable for smart contracts, but you will also be able to just take existing code bases for libraries and bind them into smart contracts. So you write your normal smart contract interface in Solidity, but then you import some mathematic library or some cryptographic library or a compression mechanism, whatever, written in other languages, and you will be able to natively integrate it and be making calls into it in zk sync. So like being separate from Ethereum gives you a leverage to be able to experiment, to add features on top of the existing compatibility. If you go for strict equivalence, you don't have this option. But if you have an option for equivalence and an option for experiments, it's interesting because we natively support account abstractions, for example, in zk sync from day one. And Argent is heavily using this feature, because it adds so much more to the UX. Being able to do multi-calls, like with a single click from your MetaMask, is powerful. Like not having to approve every single transaction, or like not having to mass approve spending of your funds for some smart contract is really powerful because it gives you the UX and security. Binding in like other languages is very powerful, etc. So like we want to experiment. We don't want to ossify now with what we have in EVM.
All right, thank you very much, Alex.
Thank you, guys.